Good morning, everyone. In today's lecture, we are going to take the topic differential pulse code modulation, which is DPCM. Now, in the previous lecture, we talked about pulse code modulation. The pulse code modulation, different samples which we used, they are not related to each other, or you can say there is no correlation between them. In differential pulse code modulation, so the past samples are used to predict the value of the next samples. So the samples of a signal are highly correlated with each other. The signal's values from the present sample to the next sample does not differ by a large amount. So you will not find much difference between the present value and the next sample. The adjacent samples of the signal carry the same information with a small difference. When these samples are encoded by the standard PCM system, the resulting encoded signal contains some redundant information bits. So in a PCM system, every sample is quantized independently, and the past samples have no effect on the quantization of the present sample, and thus the resulting encoded signals contains redundant information. So what means here is that these samples are generated, and you will find some redundant bits, means reappearance basically in these two. So due to which this system requires larger bandwidth. So this also does not comply with your Nyquist system. Proper exploitation of redundancy in the Nyquist samples can always lead to fewer encoded bits. That's why we use a differential pulse code modulation in which the past samples are also considered for this. Where and now is based on the quantization of the difference between a sample value and the prediction of that sample value using the previous sample values. Since this difference, prediction error is much smaller than the sample value, fewer bits are required to quantize it. The prediction may not be exact, but it is very close to the actual sample value. This means that the DPCM can achieve performance level at lower bit rates than PCM. So we have a sample input with that sampling interval TS, and with n bits, then we have a summer here. It goes to the quantizer. So in a PCM system, you will not find this part, this bottom part. So what's happening here is that we are getting a quantizer output, and we are using this and this predicted value here, and it's going into the prediction filter, and they are looping back into this can say summer or the comparator here, because we are comparing these two values here. So we are using the term here as comparator. And then it is going through the quantizer. Then this value is encoded, and then we are getting a Dpcm data sequence. So suppose a message signal is sampled at a rate fs equals to 1 upon ts to produce a sequence of correlated samples per second. This sequence is denoted by m and ts. The fact that it is possible to predict future values of the signal mt provides motivation for the differential quantization scheme. In this scheme, the input signal to the quantizer is defined by E and TS is equals to M and TS, M and TS cap, which is the difference between the input sample and a prediction of it. So the previous value is predicted. So this previous value is predicted on the basis of the previous samples. The difference signal is called the prediction error, since it is amount by which the prediction filter fails to predict the incoming message signal exactly. The predicted value is produced by using a prediction filter whose input consists of a quantized version of MNTS. So if you see the figure, by encoding the quantization output in figure, we obtained a variation of PCM, which is known as DPCM. Now this encoded signal is used for transmission. The quantizer output may be expressed as EQNTS equals to ENTS plus the quantized value, where QNTS is the quantization error introduced by system. From figure 1, we can also say that the quantizer output is added to the predicted value to produce the prediction filter input. So this is your MQNTS is the predicted value of the sample plus the quantization error introduced by us. So after some mathematical manipulations, we will get MQNTS will be equals to this plus this, or we can say that MQNTS will be equals to, basically this is equals to this part. So we can say MNTS plus QNTS, which represents a quantized version of the message signal that is irrespective of the properties of the prediction filter. The quantized signal at the prediction filter input differs from the sampled message signal by the quantization error. Accordingly, we can say if the prediction is good, the average power of the prediction error ENTS will be smaller than the average power of MNTS, so that a quantizer with a given number of levels can be adjusted to produce a quantization error with a smaller average power than of MNTS, where quantized directly using PCM only. Now at the receiver, we have a decoder. Earlier we have a decoder followed by a filter, but now we have a prediction filter in between that, which is used in the form of a feedback. So it consists of a decoder to reconstruct the quantized error signal. The quantized version of the original input is deconstructed from the decoder output using the same prediction filter in the transmitter. So we are using the same prediction filter which is used here, because the transmitter and receiver talk to each other before they start transmitting the signal. In the absence of channel noise, we find that the encoded signal at the receiver input is identical to the encoded signal at the transmitter output. Accordingly, we can say that the corresponding receiver output is equals to MQNTS, which differs from the original signal MNTS only by the quantization error, which is introduced by us with the help of a prediction error signal. Finally, an estimate of the original message signal is obtained by passing the sequence through a low-pass reconstruction filter. Advantages of Dpcm over PCM: number of bits used to represent one sample values are also reduced compared to the PCM. Bandwidth requirement is less as compared to PCM. Quantization error is reduced because of prediction filter. Thank you.